media or new ways of communication between each other, between us. And as you know, I mean, ICNC and ELSA followed it are based on essentially interdisciplinary communication. And after about 20 years of trying to study the brain together and educating many good scientists together, I think it's about time that we should try to really communicate in the sense of challenge each other. And so we decided together to start this new course, seminar, forum of whatever we want to call it, where we'll try to bring together experimentalists and theorists to have some sort of common denominator or common interest. And actually, I think in the case of Eli and me today, it's going to be maybe too common because we talk too much to each other, so it's going to be a little difficult for us to surprise each other. But the idea is really to really try to identify those points where experimentalists need theory and theorists need new experiments. And it has several goals as far as I'm concerned. First of all, it's really I believe that science with no theory is dull in some sense. It can be very rich in terms of facts and things to know, but as far as really making progress in what we call understanding, I think that theory is really essential. And I think we all understand this, but at the same time, neuroscience and brain sciences in general are founded on disciplines which have no real theory in the sense that I will describe in a second. Although slowly getting there, but if you're asking me, biology, for example, has no theory. I mean, it's theory-less science. It's not only biology, it's true for about many other disciplines. It's theory-less in the sense that it's hardly the case where theoretical concepts or theoretical ideas are really driving the science forward. And I believe that it's really driven by experiment to a large extent, and sometimes there are high-level concepts that really allow us to think ahead or to put things in some sort of perspective, but theory per se doesn't exist as far as I'm concerned in biology, or at least almost. And so the idea of this series, this experiment, is really to try to bring us together again and to really sharpen the boundaries and what we call the interface. And if you ask me what is an interface, and why interface? So interface is defined as the surface forming a common boundary between adjacent regions, bodies, substances, phases, or so on. Or if you want a point at which independent systems or diverse groups interact. And this is really, as far as I'm concerned, is really a good name for what we're trying to achieve here. Because after all, experimentalists and theorists are different. They're entirely different. They're different types of animals in the way they think, the way they conceive things. It's almost as bad as men and women exactly. Really very different. But
well, men as well women.
Not that bad. But so Eli and I agreed to be the first victims of this experiment. And of course, just as always, when you first try things, you make all the possible mistakes, and I'm sure that we'll make all the possible mistakes. But the idea is somehow to establish some sort of a standard for an ongoing communication, which will eventually lead not only to new thinking, but to new ideas for PhD physicists and students. And this is really why we're here, and why we call it a course, because we really want somehow eventually out of such a discussion to get out with questions or themes or new ways of thinking about the future of brain science, if you want, or the things that we hope the students here and in the next generations to do. So these are supposed to be, in some sense, what we were trying to achieve, let's say, in this big Future of Brain Science meeting that we had a month ago. Really future-looking thinking. And in that sense, allow ourselves to be a little less solid and careful than we usually are, at least, let's say, Ellie usually are, usually is. I mean, I allow myself to be very wild in my ideas all the time, but anyway, but trying to somehow really propose visionary ideas which will lead eventually to new types of work and new PhD theses. So this is more or less the list that we know now of the people on this course. It's not going to be about once a month, and so far we managed to couple more or less according to some sort of logic the following people. If it's going to work with all of them, or it's going to work with some of them, we'll see at the end. But the dates of these three are not fixed yet, but I'm sure that now that we advertise them, they will immediately tell us when is it going to be, sometimes in next semester. But as you see, we even just among us, and this is actually quite impressive, just among the LSEC and ICNC members, we managed to really cover many different types of interfaces between theory and experiment. And hopefully this will yield a lot more. And of course, if we'll continue this, we'll have to recruit other people from other places. Okay, so before I let Ellie, so essentially the idea is that we try to challenge each other. I mean, I should pose. I mean, of course, we can't expect a theorist to explain experiments. In some cases, this can happen as well, but the idea is really to challenge each other in the sense that here are some ideas that I would like to test experimentally, and at the same time, the experimentalist should tell us here are some facts that I can measure it and see clearly that I don't have any explanation. Would love to see a theory of. So this was essentially the instructions that we gave everyone. It's not that easy to switch hats. I mean, to really think, to take a theorist and ask him to think like an experimentalist and vice versa. So to some extent, I'm not sure we're really going to do it today, because obviously we all fall back into what we know and what we talk about all the time. But still, at least through the discussion and through your questions, I hope that we will achieve it eventually. Okay, so allow me just to give my own personal perspective about why do we need theory and what theory is all about. I'm sure that some of you here will object to it immediately. So if I ask you, what is this? Of course, many of you know already. So this is, anybody who ever looked under the hood of his car, this is an engine, okay. A very more or less standard 4-piston gasoline engine, so internal combustion engine. And if we just see something like this and ask you what is it, of course, there are many ways to go around, and the standard way is really to take it apart. Essentially, okay, look what it is made of, and of course then I give you a long list. Even if you're not an engineer or design, but if you're really trying to understand what it is, you just found something like this, have no idea what it's for, and just taking it apart, and eventually I can give you a list of hundreds of pieces, maybe thousands of pieces, give each one of them a very fancy name, maybe in Latin if you want, and then call myself an expert to this device or this machine. But is taking it apart really giving us a real understanding of what's going on there? So of course, even if I give very long names to all the different pieces, this on its own does not constitute what I consider, and I think most people will consider understanding of an engine. And this is more or less obvious the way I say it, but maybe even it's a little bit ridiculous the way I say it, but this is precisely what biology is all about. More or less. Of course, it's not entirely true, but you're just breaking the pieces and try to identify the different screws into different nuts and so on.
Oh, but in biology, you take the head gasket.
Yeah, so eventually you call it a head gasket, okay, when you actually know what it does or what I'm trying to say. Of course, I'm taking it to a little extreme, but eventually you need something else which will put these things together in some organized, in some meaningful way which will allow us to understand that there is actually a moving piston here that is generating pressure and so on, and some fuel is turning into very complicated chemistry to energy, and this energy is turned into force and mechanical work and so on and so forth. But without these higher level concepts, which I just list through with you, and some of them you know, some of them you don't know, like energy, force, mechanical transformation of heat to force and so on, there's absolutely no way you can really understand what this is doing, even if I give you a very, very long list of all the pieces. What I mean by that is that this way of reduction into small pieces is definitely not enough to constitute what we call understanding. And of course, when we look at where theory is successful, I think you will agree with me that essentially really one example, maybe 1.5 examples in science where theory is really deeply part of the story. You can't really think about this type of sciences without theory, and these are essentially physics and a few things that followed it, and the computer science maybe. The reason I say maybe because the computer science is too young and too avant-garde in its structure. I mean, it's trying to do everything different. It's really hard to say that it's exactly the same type of relationship between theory and experiments in computer science as we have in physics. But in physics, I think we have 400 years of history of what theory is good for. And again, let's see what are the main achievements of theory in physics, for example. So first of all, it's the emergence of very simple, what I call model examples, like the mathematical pendulum or the ideal gas, or the I like to go towards thermodynamics or something like the Carnot heat engine cycle and so on. The things that actually are underneath this understanding of engines in general. And of course, behind them, and immediately behind them, which really what constitutes the power of the theory, are what we call concepts. And these concepts are entirely non-trivial. These are things that took hundreds of years to form. And in physics, there are things like, which we take for granted now, maybe like force, or like mass, or like charge, or like energy, and so on. And some of these concepts are so difficult that it takes us years to actually teach students to understand them. What do you mean by entropy? What do you actually mean by temperature, and so on? And we need a lot of sophisticated language to actually explain them. But without them, and not only without them, without what we call quantitative relations between them. It's not only that we know how to define mass, although it's actually very hard to define it from first principles, just as it's very hard to define charge from first principles. If we don't really know what it is, if you really ask me all the way down in a philosophical sense, but we know how it interacts or what role it plays in some sort of quantitative relationship with other things. So we have equations that connect, let's say, force and mass and acceleration, or that connects charge and force and energy, and so on and so forth. And those quantitative, those can be equations. They can, in some not so lucky cases, we only have bounds, or we have tendencies like entropy tends to grow in an isolated system and so on. So some of those relationships are not that precise, or not always that precise. But without them, without quantitative relationship between concepts which emerge from some deeper understanding of what we see, I don't call it a theory. And it's actually something which really computer science puts on another type of quantification and theory. It's not enough to have equations. It has to be solvable in some sense. It has to be tractable. I mean, the fact that I can actually write down, let's say, field equation or string theory or something like this, which will have very nice and very elegant concepts, if I can't really turn them into some sort of useful predictions, in some sense useful, and computer science useless. And in some sense, computer science told us that writing the equation or even prescribing an algorithm for calculating things is not always enough. I mean, you need to be able to, it has to be tractable in some very fundamental sense. So these two things are really essential. I mean, some quantitative relationship and some way of solving them or getting some non-trivial predictions. And usually we can do it for very simple cases. I mean, only idealized in some sense of really simple cases. And of course, such equations are known to all of us. I mentioned a few. And these are really great successes of science. I mean, we really understand to some extent the basic laws of mechanics. We really understand this, in some sense, the basic laws of equilibrium thermodynamics, we understand the basic laws of electromagnetism and so on. But surprisingly, or maybe not so surprisingly, the number of different concepts that underlie essentially everything that we know in physics is extremely small. I mean, we can actually list on one page all the fundamental concepts of physics with a lot of space left. And even if I just with a little more pressure, I can even put all the equations there. Maybe even another page, but not much more than that. And this is really a remarkable story. There's a way of actually putting everything that we understand in a very few lines, and eventually get something useful out of it. But something we have to remember. I mean, moving from this very simple, very concise, very condensed way of understandable laws to what we may call understanding complex behavior like the brain, there's hardly any example for this, as far as I'm concerned, in physics. I mean, we can't even solve exactly very, very simple physical systems like a double pendulum I mean, it goes immediately to very complex behavior which is non-tractable in the computational sense. So essentially we believe we understand the principles, but we don't really have a prediction and the ability to predict the behavior of truly complex systems. This is what I think. So we believe we understand the laws of mechanics or even the laws of quantum mechanics, and through this we believe we understand the principles of chemistry and biochemistry and maybe a lot more than that, but we are not really able to use those equations to really give you concrete predictions of any real complex system. We can approximate, we can do all sorts of useful tricks, we take all sorts of limits, we can take all sorts of asymptotic behavior, equilibrium behavior, and so on. But in general, those laws are not tractable for really complex behavior. By the way, I wrote here that there are clearly examples of things which are not theories in that sense, and Darwin's evolution, in my opinion, is not a theory. It's a very deep concept and a very useful guiding principle, but it's not a theory because it doesn't even have a clear quantitative concept that it has some relationship with it. But of course, we may, and hopefully within our lifetime, even have some sort of real theory that predicts or fulfills Darwin's principles of evolution. It doesn't mean it doesn't have a theory. So again, this is something which I really usually quarrel over with Idan and people like him. There's no real theory. I don't think we can have a theory of really that can in any way can give detailed prediction of any real complexes. So something like predicting how I will behave in the future is something which is not going to be achievable by any theory that I can think about, and I think this is not a valid goal of a theory. So what you're really after are quantitative concepts that are first of all measurable in experiments, and then either empirically or through some analytical analysis have some quantitative relations that allow us to make new predictions. That's what I want from a theory. Okay, so again, the examples are clear. I mean, so again, the pendulum, the mathematical pendulum is a very nice idealized system which we more or less or even exactly understand, but we understand it only because we are able to make all sorts of idealization, ignoring friction, ignoring the mass of the wire, and so many other things, and eventually have very clear understanding. By the way, this particular system really led to some sort of deep concept. Essentially, in order to understand the pendulum, the simple mathematical pendulum that Galileo started to look at, really need to understand the concept of force and mass and acceleration and kinetic energy and potential energy and maybe gravity and so many other things. So and eventually make some useful predictions like the fact that approximately the period of the pendulum depends only on the length of the wire and gravity and nothing. I like the Carnot cycle, as you know, because I believe that something like this may be useful to think about the brain, and I'll come back to this later. The Carnot cycle is again an excellent example of an idealization of this piston in the engine, which eventually allowed us, using very simple principles like the law of the creation of gases, of ideal gases, to eventually understand something much deeper about the way heat, first of all, the fact that energy is somehow preserved, and then that it can be transferred to some sort of internal degrees of freedom that we call entropy, and so on and so forth. we can do it only by some sort of an abstraction or reduction of a very complex system into a very simple, tractable model that eventually allow us to extract some new concepts and get some new understanding. And this is precisely the kind of thing that I would like to see for the brain. That's what I am after when I talk about the brain. In other words, something like the Carnot cycle. Of course, it's not the Carnot cycle, but something as simple and as insightful in terms of understanding the basic quantities that we will eventually be able to connect to some sort of quantitative relationships. Okay. So I'll actually stop here, because from here on, I of course I'll just tell you what I consider the Carnot cycle of the brain, which is essentially this more or less quasi-static or quasi-stationary equilibrium that we have with the environment. And this type of model, it's really a toy model, it's almost a caricature of the brain, allow us, I think, to make interesting predictions. But eventually, I will not go into these things. The question that we pose here for this particular discussion, or what I call my primary challenge, and the challenge to myself as well as to the experimentalists, is to understand the emergence of what we call cognitive, perceptual, and behavioral hierarchies. And I'll say a little more about this later on. But I think this is a very good question. I mean, this is a question that, at least, I believe we can formulate, conceptualize in the sense of understanding the emergence of cognitive hierarchies.
It's a challenge. It's not a question.
Challenge. Yeah, it's a challenge. Or it's a question. It's a challenge, if you want to. How do they form? And in particular, what we want to focus here today, mainly because both Ellie and I are interested in this for many, many years, and we think it's a very good model for a lot of other things, is to understand the auditory perception. And in particular, in this context of emergence of hierarchies, we want to understand what Ellie is going to call how sounds are perceived as complex things like ideas and music and other things like this. The emergence of language. If you want one question that I'm going to address later on is what really stands behind this miracle? Why did we begin to speak? So, of course, the why and how are going together with me. It's deeper than the how. But it's really, I'm trying to understand how, well, of course, you know more or less where I'm going, but what I want to argue is that there's something very fundamental in the structure of our brain that is really this chunking of objects of perceptual and behavioral, most or maybe objects that eventually allow us to form concepts in our brain which are very similar to what I just said about science. I mean, we have conceptualization of higher and higher and larger scales, which are eventually led to what we call language. And language is in some sense not only an object of research on its own, but really a metaphor for science and the way we understand things in general. That is the way I think about it. And I would like, in the second half of this discussion, to pose some concrete experimental questions that are posed by this line of ideas to people who deal with language in particular. Okay, so I'll stop here and let Ellie tell us the other side of the story, and then we'll exchange some views.
Hall full of people. So I actually want to start by making a point that's not directly related to the interfaces, but rather to something that struck me now in Tali's talk, and this is the fact that he showed you a picture of an engine and told you that you all know that this is an engine. So I wanted to start with this. Okay. So those who don't read French, what's written here below is that this is not a pipe. Okay, that's Magritte's painting. And the question is, why is this not a pipe? And there are many reasons, but one of them is the fact that it's a painting, it's not a pipe.
It's a projection of the painting.
We'll get... okay? So when we do an experiment, the only truth that we have is the electricity that runs in the wire through the electrode that we had on the head of the subject. Okay, this is, in a way, that's the pipe. Okay, everything else that we do out of that is not a pipe. It's our interpretation of the data, and anything that we do, every paper that's written is actually heavily influenced by the imprecise and very often not explicitly formulated assumptions and ideas in the head of the experimenter. Now, I'm not trying to say that science is subjective. It's not. Okay, but we have to be aware of the fact that when we do experiments, they never live in a really model-free world. Okay, so what theories do we need? I mean, Tali asked me to try to tell him what type of theory that we will need in order to do research. So, what theories do we need to do auditory research? Here's the auditory version of the Magritte painting. Okay, it would be possible to describe everything scientifically, but it would make no sense. It would be without meaning, as if you described a Beethoven symphony as a variation of wave pressure. So what I would like, I mean, my goal... by the way, do you know who this is? Okay, I would like to prove that wrong. Okay, so that's the...
Especially last night.
Yeah. Okay, so my point is the following. When we have sensory stimuli, we get proximal stimulus. We have a sound waveform that vibrates the eardrum and eventually becomes vibrations in another place in the ear and electricity and everything. But this is not what we perceive. When an animal goes out in the world, when you listen to my voice, you don't hear the vibration of your babular membrane. What you hear is my voice. So in the first part of my talk, what I want to do is to push this a little bit further. Okay, at the moment, the challenge I would like to pose Tali, okay, is to give me a theory that will start with a waveform and end up with what is the meaning of that waveform for the animal that listens to it. Okay. Now, of course, this immediately goes out of pure auditory research, okay, because meaning the sound waveform by itself doesn't have any meaning, as Einstein said. The meaning has to do with relationships in the world. So this is, again, that's an example that I like because I dislike so intensely this painting. This is Chagall, okay? It's called the White Crucifixion. And the reason that this painting would strike very strongly most of us sitting here is because of the symbolic, because he uses the figures in the painting in order to evoke very strong things that are not in the painting itself. Okay, so Jesus on the cross, the talit, symbolizing the Jewish person, okay, the pictures of pogroms, the paintings of these Jews in Russian clothing, and so on and so forth. So all of that is outside the painting itself, and the painting, the meaning of the painting has to do with the fact that it concentrates all of these meanings into such an intense experience. So meaning has to do with the relationship between the sensory stimuli and other stuff. Okay, and one step forward in the direction of understanding, I think a wrong step, but at least a step forward, is this idea of direct perception. The fact that at the level of perception, you don't perceive the proximal stimulus, but the distal world. Okay, and I want to illustrate that This is an example that I showed, and I mean many of you already heard it. What did you hear?
Sorry.
What?
What's a sorry?
You also see it.
No, but what did you hear?
Spectrogram.
What?
The spectrogram.
No. What did you hear? Okay, people laughing. Okay, that's what? Okay. Chaim heard dogs barking. How many dogs? Male, female dogs? Okay, the point is that what happened at your ear is a waveform which has ups and downs and changes very fast, so you can't really see the details. That's a spectrogram, and frankly, I wouldn't try to. I can't read this spectrogram. I mean, there are people who can read spectrogram of speech, so they can look at spectrogram and tell you what the speech was. Okay, I don't think they would be able to read that spectrogram, although I haven't tested anyone who's really good at spectrogram reading. But both at the level of the waveform and at the level of the spectrogram, there are no people laughing. Okay, so the people laughing is something that comes far above the representation of the sound itself, and it's, at least its representation early in the auditory system. Okay, so here's the question. What are the auditory objects of perception? Okay, what are these things that when we start from the sound waveform, what are the things that we eventually deal with when we talk about the perception of the sound rather than with the physical waveform itself? Okay, so the problem of defining auditory objects is the problem of defining something that would take sounds and parse them into bits that make sense. Okay, and make sense again. That's where. What does it mean? Make sense. So one way is to go in the direction of direct perception and say that these bits should correspond to things in the world. Okay, I think that's not. In a way, that's not good enough because of the ecology of sound. I mean, there are too many sounds that can be emitted from all kinds of strange objects. I wanted to. Yesterday, my 12-year daughter showed me a movie.
תזהר, אייל, יש מלא רציפים של על כוס, אל תדאגרי, שום דבר לא יפגע בי.
נו, ומי עשה את זה?
זה אני.
קוטרננה.
מה? זה לא אני.
כולם יודעים.
Okay, and so on and so forth. Okay, so my point is that okay, we are obviously not going to take all of these songs and attribute them to the actors in the movie. Okay, when we see this again, there's a lot of interpretation going on, but you would, although the movie is made so that there will be some sort of illusion, what you really do is attribute the sounds to the singer, to the famous singer, or to the known singers of songs that, not to me, but that that are referenced. Okay, so auditory object as representation of sound sources is, in a way, that the definition is too weak. Now, one direction in which we go in the last few years is to try to go with identification of auditory objects with predictive representation. So the idea is that you need something in the head that would allow you to predict what happens in the sensory world a bit later, And if the prediction is good, you have a good representation of the world because you know how it, you know how it, what is going on. If there are errors in the prediction, then you have to try to modify the model, and then you have a lot of all kinds of processing that goes on in the world.
May I ask a quick question here? Why not post-predictive representations?
It doesn't really matter. I mean, the thing is that as far as I mean, the
predictions, but it can be not necessarily later. Predictions about the world. Is that what you're saying? Yeah. Why it's important that it's later, not in the
well,
past?
because sound,
especially other parts of the world.
No, yeah, okay. This is specific because sounds develop in time. Okay, so
but
naturally.
you want to say something about the sensory world is not necessarily the sensory auditory world.
Okay. I should have written the auditory world.
Okay.
This is specifically for audition. Of course, if you talk about a sense like vision, where you have spatial relationships, that would be good too. Okay.
Actually, I would argue that it's always temporal. Maybe later.
Okay.
No.
Even when you look at an image.
I agree with you. I mean, that should be written here auditory if we want to do the prediction in time. I mean, prediction are also good for visual. Temporal prediction are also good for visual, but they are certainly not the only type of prediction that would work. Okay, so we have some evidence for predictive models in the auditory system. I'll show you very fast two types of phenomena. So the first one is the type of experiment that we've been running now for over 10 years, where we play a common and a rare sound, and the response to the rare sound is large, and to the common sound is smaller, and then we do all kinds of controls, like reversing the roles. So here the low frequency sound is common and the high frequency sound is rare, and then the sound that's rare, okay, F1 here, evoked larger response than the same sound when it was common. Okay, and the sound that was rare here, this is F2, evoked a larger response here when it was rare than when it was common. Okay, and we can play them, do other controls as well, and the final result here is the fact that the same sound evokes different size of responses when it comes in different context, and the response is larger when it is rare than when it is common. Now, this requires a lot of additional controls. Okay, this is just a demonstration of the basic phenomenology. Okay, these are, by the way, intracellular recordings in auditory cortex of anesthetized rats. Okay, they were collected by Tai Herschenhorn in my lab. And one attempt to explain this data, done in collaboration with Tali and Jonathan Rubin, is to actually take this view of the world as looking at the past and trying to make predictions of the future, and a bit seriously. So the idea is that you use the past to construct some representation. So here, for example, I have a past that consists of the last 5 sounds in the sequence. Okay, and I have a simple model. This is a model for an animal that can't remember a lot. So in this case, it observes the past and it remembers only 1 or 3 things, whether there were 0 or 1 red tones, 2 or 3 red tones, or 4 or 5 red tones. Okay, and once I have this representation, I can calculate what should be the probabilities assigned to the next tone in the sequence, and then I can these probabilities will be used to check the prediction, if you wish. Okay, so the beautiful thing here is that Tali can take this example and actually calculate good models. Okay, good models in the sense that they balance the complexity of the model with how well it can do in the prediction, in predicting the next sound. And we can take these models Okay, so we have here the amount of surprise, how bad the surprise is for a specific sequence of sounds and the actual responses of the neuron, and we can see surprise here is a kind of prediction error. Okay, it's large when the probability of the next that I thought the next tone will be small, and it's small when the probability that I assign to the next tone is large. Okay, we can see that the responses to the same tone are related in some way to the actual, to this surprise that was calculated purely on statistical grounds based on first principles. Okay, so this is one kind of prediction. Here, the sounds are running at about 1 per second. Okay, so I'm looking at the last, let's say, 10 seconds of the world, and I'm predicting what will happen in the next second. Here's another attempt to use predictive models. Here we tried to account for an experiment, a human experiment. So the experiment is a detection of voices over over musical instruments. So a subject sits, it presses a key, and it hears a lot of wind instruments. And from time to time there's a voice, and when there's a voice, you have to release the key as fast as you can. Okay, and what people measure, what the people who did this experiment measure is the reaction time. So when in blocks, when we have voices over instruments, you get one reaction time, and if we have string over wind instruments, you get a longer reaction time. Okay, so there's something that's it looks like there's advantage for the detection of voices over other musical instruments. And what these people, by the way, it's Daniel Persnitzer and his group in the École Normale in Paris, they showed that, I mean, this reaction time task was done with relatively long sounds, about 100 milliseconds, but in fact, in order to detect the fact that the segment is a voice and not a string instrument, you need only 8 or 16 milliseconds of sound. Okay, so what Yael Bitterman did was to take all the sounds that participated in this experiment and create a predictive model out of that. So basically what the model does is to use, that's the best linear model that would take a segment of one of these sounds and predict the next sample in the sound. Okay, so we can do that to the sound. So we have the original sound, we create the prediction. Each sample is based on the previous real sample that occurred in the sound. We can compare the prediction with the actual sound, and what we find is that the predictions for voices are the worst. Okay, so these are correlation coefficients between the prediction and the actual sound, and the voices are actually the worst. And what Yael showed is that if you just collect prediction errors, it's enough to collect prediction errors over about 10 milliseconds in order to get a significant larger errors for voices relative to strings. Okay, so even at this very fast time scale, a predictive model is capable of doing something that looks like what humans do. Okay? And it can extract the differences between voices and string instruments, those that have been used in this experiment. Okay, so what I did was to say in a very undefined way that I want to start with a theory of meaning out of sound. Okay, and now what I'm really saying is that what I would like is to have a theory of forming predictive models on the fly from the sensory input. Okay, so and these models have, in a way, to be very robust and calculated very fast, because we know that we can update them within less than 100 milliseconds under the appropriate conditions. And they must be hierarchical, because I showed you that they occur at multiple time scales. Or they might operate at multiple time scales. So I would like a model like that to be able to tell me things from 10 of milliseconds, which allow me to identify different the voice versus instrument, to the tens of seconds that are necessary in order to get the meaning of a spoken sentence. Okay, and in the last 5 minutes, I want to go from here to the other side of the story. All I said now, everything that I was saying, it was done in a way passively in the head of the animal, but what we would really like at the end is not only to have a theory that will tell you what the meaning of the sound is, but also how this meaning is extracted by brain. Okay, now here I have much less to say. Okay, yes.
But when you say meaning of a sound, and it sounds like the meaning is not in the brain. The sound has some meaning. The sound has only meaning to you, right? I mean,
Yeah.
So what do you mean extracted by the brain? Or
Okay,
by the
so
brain?
you need
This sentence means
this is an experiment. Yeah,
epistemology.
experimentalist. I'm an experimentalist, not a theoretician. Okay, so I know what I mean in a very rough sense. Okay, what I mean is that I have an environment. Okay? I'll say that. I mean, I'll get it to the end. Okay, I somehow what I want to do, okay, is to create a situation in which sound. Okay, let me start by what I don't want to do. Okay, and then we'll get to the. Okay, this is what I wanted to say here. Okay, so most sensory experiments with behaving animals look like that. Okay, you select stimuli, okay, 3, 4, 10, in the best experiments with maybe 100. Okay, you train the animal to discriminate between them. Okay, then you go to your favorite brain region. You record from enough neurons to show that the neurons can discriminate between these sounds, and then you publish. Okay. And you say that you found a neural substrate for sound discrimination. Okay? Now this is obviously wrong, because the best place in the auditory system to do sensory discrimination is the auditory nerve. Okay? Actually, the best place to do auditory discrimination is in the loudspeaker, that's outside the brain. Okay? So in a way, the standard way of doing sensory experiments is, first of all, trivial in the sense of what the brain has to do, and secondly, going to the wrong place in order to get the auditory, the neural responses. Okay, so this is, in a way, what I think is not the way to go if you really want to understand what the auditory system does in real life. Okay, so what do I have? Yeah.
I'd like to comment that I think that it's very important what kind of readout you're using. So in order, I don't know about vision, but in order to understand the picture, when looking at the retina, or to discriminate between people and cars, when looking at the retina, this is difficult. Readout is very complicated, but doing it in IT is much easier. In the sense that you may have a linear readout.
Yeah, but when you ask about discriminating between cars and faces, you don't talk about 10 stimuli, okay? You now talk about thousands of stimuli. And that's a totally different question. That's a question of generalization, not a question of sensory discrimination. Most experiments, the way that they are run, they really test discrimination between in the auditory system, okay? Between a small set of stimuli, not about things like discriminating faces from categories. Okay, category discrimination is a totally separate story, and this already approached the issue of meaning. Okay,
so your criticism about low-level things, like high and low pitch or something like that.
Yeah, for example,
people laughing versus.
If you test, when you test the right ability to discriminate between a sequence that is 5 times G and 2 times D versus a sequence that's 7 times G, okay, you are doing a simple thing. Okay, that's a simple discrimination task. The task itself doesn't have, it may be that you want to see how information is integrated across time, or how attention has to do with it, or all kinds of things like that. But the sensory task itself is trivial. Okay, you don't need all the brain up to the hippocampus or whatever to do it. Yeah.
So, since we have computer software that does a lot of these things, so voice recognition, even with music, if you just play a very small segment of the music, it tells you what the song is. And you get these in cell phones and so forth. So in an artificial sense, in a number of cases, we have relatively good working software. So would you call that understanding, or would you like to comment on how that?
Software, I mean, my perception of software sound cognition is actually, I mean, is not very high. I mean, this automatic speech recognition is very bad, and
No, not anymore.
And if it will be better?
Yeah. So it, presumably it will encapsulate some of the things in order to do the thing to the brain. Yeah.
Like computer chat playing.
Well, that's it starts to feel like
they're doing very good, very well.
I feel a little bit like your Rabbi Yirmiyah kind of story. Okay. Let me finish and we'll go. Okay. Right now, I'm not asking about how computers do it, but how I, as an experimenter, try to understand how the brain of the rat is trying to do it. Okay.
But
yeah.
answering the questions you asked, and obviously it's more interesting to look at more complex parts where you need maybe larger parts. But why this has to do with, behaving animal in natural environment? Necessarily.
No, it doesn't have necessarily. No, it doesn't have to do necessarily with behaving animals. What I said is that one of the issues that you want to do when you study the brain. Okay, when you study the brain, you might be able to understand how the meaning is extracted in the brain. Okay? I don't have anything against machines trying to extract.
No, but I'm talking about discrimination between cars and airplanes extracted from the neuronal response as, let's say, an IT in a measured animal.
No, that's okay. I mean, that's what I'm doing for life today.
And that's not meaning extraction in the brain.
It is, but that's
so
no. But then
the organism, maybe.
Okay.
Something else.
Okay.
Something else.
That's fine.
Okay.
No, what you don't define is really meaning. Is a meaningless word in that.
I would. Okay. I still didn't say what I want. I still didn't say what I want to do.
Okay. Behaving animal in a natural environment.
Okay. So I would like. Okay. So I would like the environment to be natural as possible. And now I will impose the meaning of the sound. Okay. So the idea is that I would like the animals to extract meaning that I put on the sound. For example, the sounds may tell, really important information. Okay, rat is supposed to be female rat. Information is supposed to be important.
But it can be completely artificial, right?
Yeah.
So you will not tell us anything about the extraction of meaning of sound in any natural setting. You can combine in a very artificial way sound to something.
Yeah, so I think
arbitrary association.
Right.
So why it's so far from extracting of meaning of auditory world?
No, I think that it's not. Okay, so I'll get to that in a moment.
And then we really have to nail it down because the word meaning here. Okay, I made
the word meaning is meaningless.
You have to put it in some context that is measurable.
Yeah. Here's something I would really like to run. Okay, so I would like to have a way of analyzing the environment plus the sound that I put into it in such a way that I will be able to calculate the population given the information supplied by sound. Okay, and then presumably I can measure the actual rate of reward accumulation by the rest. Okay, and from that I can try to deduce how well they exploited the information and how they actually understood them. Okay, and then I can stick electrodes into auditory system or a bulb or hippocampus or whatever and try to see how this is done. Now, in a way, okay, that's the goal. Okay. So speech is arbitrary association. when you do speech, you do arbitrary association between sounds and meanings. Okay, and that's, in a way, that's what I would like to achieve. Okay, that's it. Now I'm open to questions, to more questions.
Before we take a break, I just want to comment that when I said that we want concepts which are measurable, and actually I think that anything which is not measurable in some sense is meaningless, I was actually very religious about. So things like meaning, consciousness, will, whatever, freedom, they're all things which, until you tell me how you're going to measure it, I don't know what they mean.
Yeah.
And therefore I don't even know how to begin to formulate a prediction or a theory.
Yeah, okay. So this is why in a way I replace meaning with information here. Okay, so the meaning, as I said, meaning has to do with things in the outside world. Okay? Not with the sound itself, but with the relation between the sound and things in the outside world. So when I create this world in which sounds tell the animal things about the external world, I'm operationalizing the definition of meaning by identifying it with information.
But the world is also internal.
Okay, I could put an electrode in the VTA if you want.
But that's trivializing in some sense.
What?
You define some internal chemical or electrical system as identified as reward, and of course it's not reward, something else. I mean, this is just to correlate. Okay.
Yeah, but I need, again, as an experimenter, I need to operationalize all the terms that we are using. Okay, at the end, I have to manipulate something and to measure something else. Okay, so the question is, to what extent this makes sense in terms of the bigger question, that's much less well defined, of in what way the auditory system is doing something for the organism in the real world. Okay? And I think that this is still something that I hope to be able to make into a controlled experiment, and that it is already more interesting than just showing that an animal can discriminate between two stimuli. But I mean, as you yourself said, at the end we need the simple cases that will be the toy problem.
No, but you know, you need the simple cases in order to understand the higher level concept, and then make some useful predictions. Okay.
Can you be more concrete about this roadmap? Like, give us I'm reading these. I apologize, but I'm reading these lines, and I can't form a simple experiment out of it. Maybe it's my personal problem, but it would be. I would like to see an example of a dream experiment where you can measure everything, and you can, and animal behaves the way that you would like it to behave.
Okay, so the environment will tell you, will be able to convey information about a number of different things. For example, where a sound source is, okay, what type of food do you have there, good or bad, and maybe about, I don't know, how long it will be there or something like that. And one thing that comes to mind is the ability of the animal to actually use all of these three pieces of information efficiently when they are conveyed at the same time. So you get a kind of a sentence. Okay, good food to the left now. Okay, and that's so. This is the kind of thing that's more concretely, I'm thinking as a first step in this direction.
So okay, so this is the framework. Now you do an experiment with two possibilities. Either the animal learns and is doing perfect, or that it doesn't.
No, I don't think so. I think that here, I mean, the thing about this experiment is that there is no right or wrong answer. How well the animal exploits information is graded, can be measured in a graded way. And it can do it, it can completely ignore the auditory information, or it can use it optimally, or it can do something in the middle, which will show me that it really pays attention only to one, maybe to one of the distinctions, not to others. Okay, and what there's the issue, the practical issue of trying to measure things, but I feel that one of the problems that I have and that I don't know how to solve is how to measure what's optimal behavior. I mean, to what extent I can really set a limit to the performance of the animal and in an interesting way and judge how well the animal does relative to that.
That's exactly what we did with prediction experiment in the auditory cortex. We actually calculated an optimal behavior, compared the animal to this, and that's why you say something.
No, the neurons don't do optimally. The neurons do.
Well, they do optimally under some constraint, which we could
yeah,
easily identify.
Yeah, but we had in that case the statistical context in which we calculated optimality was very clear.
But you're asking about optimality of behavior.
Yeah, optimality of behavior.
Not of the
Sure,
yeah.
so we can address this as well. But
yeah.
All right. I think what we want to do now, essentially, I want to actually try to pose a framework that may or may not lead to some possible answers, but eventually I want to put some quantitative challenges back to the experimentalists. I mean, this is really what we want to have here. But I think actually we can say a lot more about the theory that goes in the direction of what Eli wants. I'm curious. I mean, speech recognition is not I can today give you a computer that does better than your rats and mice in terms of understanding speech. But that's not satisfying.
Oh, that's not.
Why not?
I'm doing better than that.
No, but unlike you, the computer is completely understood. I mean, in some sense, I know exactly why and how it does.
Yeah, but okay, my.
No, there's something
speech understanding. Okay, speech understanding in the sense that you're talking is like face under face. In a way, it's categorical distinction. Okay, you have a set of waveforms that mean one word and another set of waveforms that mean a different word. Okay, and so it comes into the same category as face against car discrimination, which is highly non-trivial. Okay, but it's a sensory categorization problem. It's not meaning extraction. The computer presumably doesn't know. I mean, speech understanding system.
The problem is not pattern.
Don't use it to guide behavior.
Yeah. Okay. So you answered it, but essentially, it's not really the pattern recognition.
Guide the behavior of wrong.
Pattern recognition.
Okay. So at the end, you'll get something that looks like that. I mean, that's. But again, I'm interested in the rats, not in the robots.
No, but again, I just want to sharpen the issue and come back to this. It's not pattern recognition per se.
No.
It's the way it is evolved and why it is evolved in animals. How again, this emergence of hierarchies. I mean, it's really the principles that eventually push you towards pattern recognition. That's the solution, but it's not the task of understanding words per se. Okay, well, come back.
Okay. I don't have any problem with this.
No, I think it needs a larger framework. It's not just designing it. If you can train a rat to recognize words.
No, to train a rat to recognize words will be easy, I guess. Okay, that's people show that rats can discriminate words. That's not the problem. Okay, the problem is to put these sounds again in a context in which these sounds inform the rat about the environment in complicated ways, in ways in which at the end, when I say teach rats to understand the language, this goes beyond just identifying the words and individual words and meaning, but also, for example, the ability, the thing that's one of the difficult aspects of language, which is the fact that you can refer to information that's very far away, the long-range correlation that you have in sentences between events, auditory events that occurred far apart in time. Okay, so this goes now beyond the ability to identify the words themselves.
I agree, but it's not said before. So it's really in the context of behavior.
So what do you think is that more complex behavior we somehow don't understand, or in principle don't know how to. Okay, so again, from the computer science, so what I was getting at is, so for instance, there's this thing called the DARPA. I mean, there's not in the context of auditory, but there's a thing called automatically through, say, urban traffic as well as through a desert and so forth. And I think Google is actually now testing cars in the United States which can drive themselves.
Just a Daphna, can you wait a moment and answer that question?
Getting back to so, are you when you say understand, or when you say meaning, are you talking about understanding or in principle being able to do it into say artificially? What is understanding? Or what is not clear to me.
I'm not trying to pose.
Let's spread it to the next. I think people either want to run away or to have a break, so we will take.
What is the schedule?
In principle, we have time until 4:30, but we're not going to take it.
You're serving lunch or?
I have another 20 minutes, and then we have discussion trying to really close the loop somehow. Because otherwise, there will not be any point of break.
Let's take a break. Oh, let's take a break. 20 minutes?
No. 10 minutes break, and then 20 minutes. The second part of my talk. I'm going to say was just an introduction and motivation to actually have some interesting כן, קצת אחד אגב, יש לי ניסוי שהוא נראה בדיוק מתאים למה שאתה עשית, אבל לא נראה שהוא ישמח אותך. זאת אומרת, יענה על השלכים. זה ניסוי שכחנו מהצד עכשיו, אבל ניסוי שבו אנחנו נמדו פה שיש סדרה של תמונות. אוקיי, אני יכול לבחור בין שתי מטרות, יש איזושהי סיפור גם לריבור בכל אחת והתמונות, כל תמונה היא אינפורמטיבית לגבי השקה של בעיה.
ואותו לימדו גם עברית.
לא, איתמר רק עליו אני יודעת, אני אשמח אם תצביע עליהם, שכזה, תצביע עליהם שותים נדב כשהם לא שומעים את תצביע עליהם עכשיו, אבל אני כבר תודה.
שמה?
שיכולים לבוא אותו לפני שהם
נעמה? נעמה?
נעמה, אני חושבת שהיא גם עבדה
יכול להיות. היא נעדה בעברית, אבל אמרו לכמה.
אני חושבת שזה השם של הבחורה הנוספת שלא התאימה. אבל אני מאוד אשמח יש לך את הטלפון שלי? לא, יש לי כאילו שלי.
אחד אומר שבאופן תיאורטי העבודה שלך צריכה לשבת, זה כל פעם להציג העבודה שלך. כן, זה לא, אחד.
All right, so I know it's a little difficult for us to really be completely original, as many of you have us many times, and the first time we really try to do this, but together with your help, I'm sure we'll be able to formulate something interesting. So I actually want to take one more step beyond what Eli already said about predictions as the fundamental theory, and really try to somehow change the culture, if you can call it this way. I mean, so in principle, I would like to avoid using words which are not well defined. I think this is something which if we ever manage to do this in brain science, it would be a great achievement. So, for example, when I use the word meaning, or when I use the word understanding, even, I mean, whatever. And of course, many other things that we use in brain science, like consciousness and free will and whatever. I mean, since we are talking about the brain, there is such an overload of concepts which are ill-posed and ill-defined that it's getting immediately into a mess in terms of what I consider quantitative theory. So I think the idea of prediction is very powerful. It's not only very powerful because it can be quantifiable, as I'll show you in a minute, completely. I mean, in some sense, in a very precise way. But also seems to us intuitively as a very powerful metaphor for what the brain is really trying to do. I mean, so in some sense, I want to take this idea of gathering information in the past in order to make useful predictions in the future and bring it down to a level of the pendulum, a caricature which is so simple that most people will laugh at it as really a model of the brain, but then I may be able to actually formulate concrete and quantifiable concepts with which I can form some equation, really an equation, and then test it in experiments. Actually, Eli more or less described an experiment like this, but I actually would like to argue in a much more, I want to take it to an extreme and see, actually challenge you or challenge the experimentalist to find examples where this is not enough. I mean, just like saying that when Newton, with all the modesty requires him, formulated his laws and said, these are the laws of the physics of the universe. I mean, S equal ma and the two others, and that's it. This was an amazingly bold step. I mean, okay, how can you say that? I mean, of course, it took almost 200 years to really find exceptions to this law, and eventually, the coverage of this type of crisp formulation of physics was amazing. So, in some sense, and I know it's really completely not only overambitious but also ridiculous. But let's try to see if we can shrink the brain to the level of one equation, almost one equation, which will do something. And it's not only me, of course, many people think today that one of the main goals of the brain is to make predictions. And it's not just, it's really, if you think about it long enough, you see that there's hardly anything in life that we cannot cast into some sort of gathering sensory information in order to make what we call valuable predictions. And the only thing I'm trying to do now is in one step, essentially, turn this into an equation. And I think this is a very good exercise. So of course, the key here is that the brain is in some sort of interaction, what we call sensory interaction with the environment. So what Eli called sensory perception is some sort of, as far as I'm concerned, some sort of channel gathering information from the past sensory perception, and in some sense, forget everything that is not going to be useful in some valuable way in the future. And of course, they're already quantified here. So first of all, there's an environment. This environment has some sort of objects, like these square colors here that I have to define. But this is rather easy. Mathematics, you can think about it as sound, you can think about it as images, you can think about them as a movement in the world. Like, I know how to think of the environment in a very simple caricature-like thing, as what we call stochastic process over some sort of discrete variables in discrete time and so on. This is easy. I don't believe we actually lose anything in terms of describing our brain when I think about the environment as very, very simple. And actually, in most neuroscience experiments, that's precisely what we do. We actually design an environment which is so simple that we can really quantify it, like the two tones of Eli, or like playing against an arm bandit or something like this. I mean, very simple experiments. Or predicting coin flips, or things which are so simple that are almost ridiculous, but we do this already. And not only that, when we do an experiment in neuroscience, we usually allow the brain to be in some sort of what I call equilibrium, some sort of stationary flow of information between us and between what we have to do with this information. So this is also something which you may not buy immediately. When you think about it, in the first 2 minutes of this lecture here, you adapted your sensory perception, you adapted your ears, you adapted your attention and so on. And from now on, you are more or less in some sort of equilibrium flow of information between me and you. I mean, you understand more or less half of what I'm saying. You got used to my very poor pronunciation and so on. And eventually, you understand enough to get something out of it. And what I argue is that this is quantifiable. There's an amount of information that I can measure that flow from you to me, and I'm your environment for this matter, and you can make valuable things with it, otherwise you wouldn't be here. At least I hope so. Actually, the way you do it is by essentially guessing more or less everything that I'm going to say, and you have some of you have a perfect guess of what I'm going to say, and they actually look only for the surprises. where he actually said something I didn't quite expect, and it happens once in a minute maybe. And this is your value, essentially, trying to extract out of the surprises the things which are really valuable. So there are two quantifiers. Again, I want to pretend to be an engineer in the sense that everything that I want to, every concept I use here is measurable and quantitative. So when I say that I gather information, I have to tell you exactly what I mean by this, and I'm going to measure it. When I say that I make valuable predictions, I actually have to tell you exactly what I mean by this, and give you an equation or a measurable device that will measure this prediction. And when I say that the predictions have value in the future, I'll actually have to tell you what I mean by this. I mean, in most sense, that has value, and this is, of course, difficult in general. And when they say that the sensory perception has costs, I also have to be very specific. So all the four terms here, essentially, I want to call this a perceptive channel. I want to call this predictive channel, and associate value with my predictions and cost with my action, and that's about it. And now I want some sort of equation to connect this. There's another quantity here, which actually turned out to be very important, and is really how the past of the environment is related to the future of the environment. This is a slightly more tricky thing, but if you think about it, the environment around us is highly predictable in the sense that you can really, despite what people say that we can't predict the future, most of the time, most of the events in the future are highly predictable, and that's why we're here. Because if the future were completely, totally unpredictable, we couldn't do anything. So essentially, I'm going to play, I've been playing this game for some time now, and I claim that actually there is a very elegant, a very simple set of equations that define an optimal flow of information from the past in terms of perception to the future in terms of prediction. And it's not much more than 3 or 4 equations I can write on one page. Okay, Elon.
The loop is not closed, so are you going to tell us what we will do with the prediction?
Yeah, the loop is closed because there's something which is called feedback.
It's not good enough for prediction. Feedback is not good enough.
Do you have anything better?
You write that your predictions generate actions. These actions change the sensing. So the loop is not closed in the right place.
No, okay, you're right. So I'm already, even in this caricature of a brain, I already make a very serious assumption, and I say it again for Chaim and those who didn't hear it before. Of course, we heard it many times before. But I'm assuming some sort of an equilibrium. So you're already in this flow now. I mean, you already heard me, you know what I'm going to say, and you're actually playing a game now that something is changing in your brain, but nothing in terms of learning is happening here. I'm excluding learning. I'm talking about the situation where you have a robot who's already well trained. By the way, exactly like most of the animals in most neuroscience experiments. I mean, you train them, they don't learn anything, and now they react to the changes of the environment.
Just I want to make a comment.
Yes.
Because there are many students, you keep saying that this is how most experiments are being done. So I would like to say that the balance is changing, and this is not so true anymore.
Okay, this is very good news.
In most cases, we try to change the steady state during the experiment to learn about this change.
No, but I think that even, of course, we're all trying to understand learning, but no, okay, so let me be a little more precise. Even, of course, we're interested in the way that the brain adapts to the environment in the learning process, but I think we are in a much worse shape in terms of quantifying this process. I mean, we have I can tell you a lot about theory of learning, but what is nice about this equilibrium picture, first of all, even in your experiments, you've trained, measure one thing, and then do some learning, and then train, and then measure other things, and during this measurement phase, you are in more or less an equilibrium. Okay? Otherwise, because you average, all of us average. I mean, we average responses. If you don't average, I'm very happy to hear this. But most of us average responses during experiments. So in some sort, it's an equilibrium in precisely the same sense that the physical device is an equilibrium with the measurement apparatus. In exactly the same sense, you measure temperature, there's some sort of an equilibrium between the thermometer and water that you measure, and so on. I mean, the notion of equilibrium actually is very fundamental in physics, and I think it's also very fundamental in neuroscience. It's not the same type of equilibrium. It's not thermodynamic equilibrium. It's equilibrium in terms of nothing fundamentally is changing here. It's a machine that acquires, measures information from the environment and uses it, but nothing in terms of learning is happening here. And I'm actually very specific about this. Now, so when you say prediction, some people say, okay, perception is not about predictions. But now we know that even very basic perception, like vision, making sense of this image in the sense of these gray pixels are perceived as a dog, this completely miraculous process, we now know that making it in a bottom-up way is almost impossible. It's actually impossible computationally. Before it was shown to be impossible. Essentially what's really happening here is some sort of hypothesis generation and testing, as Merav can easily tell you. So essentially we don't really see the dog, we hypothesize the existence of a dog, and then we actually test this hypothesis. So essentially perception is active in the sense that we always guess, hypothesize about what is there, and then go back in some sort of reverse hierarchy, as of course is well known from this picture, for example. Instead of, we don't really generate, in a generative way, generate the senses from bottom up to top down. So we first guess there is a face, or there is a tree, or there is a house. And how do we guess? Essentially, there's a prediction machine there. That eventually that is generating those hypotheses. And what the sensory system is largely doing is actually testing this hypothesis on the lower level. So if there's a dog, there should be ears and mouth and whatever, some very few features that if I, some first checklist that if I check all of them, there's high likelihood there's a dog. And we know that hypothesis testing is a lot more efficient than generative modeling. So it's something we learn from computer science, from pattern recognition. Generating hypotheses and testing them is infinitely, exponentially faster than trying to learn all the possible objects from script. So this is, it must be, and this is exactly what John Sossos said in 1990 already, vision cannot work bottom up. In no way. So this paradigm of David Marr and others cannot work. And now we know it's not only true for vision, it's true also for auditory perception.
David Marr is bottom up.
Sorry?
David Marr.
To a large extent. I mean, he really said there are features, low-level features that organize in a feed-forward way, and eventually somewhere up there, the high-level concepts emerge. And actually, we just heard 2 years ago, Tommy Poggio still saying the same thing, to my surprise. But most people don't believe it anymore. Yes.
But how is feedback and hypothesis testing gets saved in Z1? Or like
well, maybe Merav can answer this. We know that you first perceive the high-level objects and only then see the details, in some sense. And the real question is, how does it happen? I mean, there must be some underlying mechanism which is working on the high level. And this is what I meant before by how is this hierarchy, and how is this hierarchy emergent of hierarchy concepts and things and sound as well. So of course, okay, I just skip this. Of course, what I mean is that we always do this. I mean, vision is about guessing and verifying. Guessing and verifying. We can't really understand these two images, for example. Many of you have seen them before. At least this one. Until I tell you there's a dog here. And then suddenly you look for a dog and eventually find it. And that doesn't make it. Or if I tell you, what is this? And if you will look seriously for a long time until I give you some hint. And this hint will generate a prediction, and the prediction will be verified, and so on and so forth.
Give me the hint. People laughing.
What is the hint?
No,
people laughing.
What is it?
So the hint here is the nude back of a woman.
And you point the details?
Once you see it, you can't get rid of it. Look, you're a grown-up. But in some sense, it's actually, I don't know, you see it? You don't see? This is the legs. This is the back. This is the head here.
Crawl behind.
Behind. Anyway, if you don't say it now, then come to me later. Now, we know that for language, this is certainly true. I mean, this is the work of Eli, Merav, and others. More, okay? About the reverse hierarchy in the auditory system. So this is actually bringing us. So we know that there's simply no way we can generate the word directly from the sound. There's not enough time for it. If I have to process it every millisecond of it, it's much easier to guess the word and then verify it and then check it. So actually, we know that this is the way speech recognition is done today when it is more or less working. So there's a language model, essentially make very few predictions of the next word, and then there is essentially some sort of statistical pattern recognition that actually verifies. So if I guess that it's either they or they, then I have to look here at the onset time of the D and the B, and that's about it. It's a very simple case. So for speech and auditory perception is even stronger evidence that prediction and the hypothesis testing is really the rule, not the exception. This is what's happening all the time. And we know it's true for music. At least we believe it's true for music, and it makes a lot of sense. But the point is that we don't only guess the next word, we really guess much more than this. We get the next sentence. We actually have a very nice idea about the next paragraph. As I said before, you're really predicting ahead of me all the time, and this active prediction of what I'm saying is really helping you not only to perceive, but eventually the amount of processing I have to do on the millisecond time scale is so slim that the whole thing makes a lot of sense. I can do a lot of things in parallel and so on and so forth. So it's not just words; it's much more than words. And so there's a hierarchy of objects, of what we call perceptual objects, that emerge and allow us to really understand each other. Now, to me, this is really the key to the story. I mean, how such hierarchies can emerge. And what is really nice is that they emerge from the same principle. If I want to make predictions about the future, I'll better think in higher levels than in detail. So, for example, I may not know exactly when, at what millisecond the next word is going to come, but I know it should be there somewhere. Well, I cannot tell you if sky tomorrow is going to be cloudy at 4 p.m. in this corner of the sky, but I may be able to say, overall it's going to be rainy or cloudy or sunny. So this is a higher level object, a higher level concept that is necessary if I want to make long-term predictions. So this is really a very, very fundamental thing. Predictions and hierarchies are very nicely tied to each other. If you want to extend your, what I call predictive horizon, see more into the future, you are forced to, what Merav calls, chunk your objects into higher level objects. So the hierarchies and the predictions, and the same true about the past, by the way. You don't have to remember everything in the past. You have to remember only a few things which really are enough to make good predictions. And again, a piece of mathematics that we understand pretty well now, and that if the environment is really more or less stochastic and stationary, then the amount of things in the past which are really valuable in the future, which has any mutual information with the future, whatever mutual information means at this point, is slim, is very, very small. Most of the things in the past are irrelevant in terms of prediction, and most of the things in the future are irrelevant with respect to the past, are unpredictable. So life is essentially some sort of surfing over this predictive part of the environment. By the way, if you're asking me, this is what saves us, because we couldn't cope. I mean, we don't have enough processing power, enough brain to actually remember everything around us. It's too complicated, and that's because only a very tiny part of it is really important. Even flies or even simpler animals, simple creatures can cope with very complex environments because they don't need most of the things that happen. Okay, so language, as far as I'm concerned, is really a window, a very important window to the understanding of how we generate these hierarchies. And that's why I encourage everybody to think about language perception and the emergence of languages. So it's not just sound, because there's something funny or interesting about language. It's not just for communication, as we usually think. It's really mostly, I think, for conceptualizing the important things in the world. And we know now, I'll just show you a few nice examples, that language is an extremely regular phenomenon in statistically. So those words that emerge in language seem to obey some very simple statistical laws. It's not something that linguists like in most cases. That's why Al is not here at the podium. He likes it, but because it goes against the nature of language as something, as a God-given phenomena that we are forced to. We must use this way, and there's grammar and syntax. If you violate the rules, you are going to be punished, and so on. It actually works much more as language as some sort of an adaptive mechanism that's changing all the time, that really allows us to cope with new things in the environment. So I'll just go show you two fascinating facts which are known to a lot of people, but are not emphasized enough. So first of all, if I ask you how many words are in let's say, Hebrew or English, I'm sure that those who never heard it before will come up with some numbers. 2 million, 100,000, 1,000, whatever. So how many words do you think there are in English?
50,000.
How many?
50,000.
50,000. Any other bet? I mean, if you take the Oxford Dictionary, there are about 2 million words there. Why 50,000? I don't know. I mean, so there's something arbitrary in whatever you say. And indeed, if you just try to measure it, again, you just look at something very simple. I'm sorry for this Hebrew. Most of you can read it, I suppose. If you just look at the number of words, I just look at very long text, let's say news in the internet, and I simply count. Whenever I see a word, so a word can be defined almost arbitrarily, let's say anything which is separated by spaces or punctuations. And really doesn't matter how you find it, with the morphology, without the morphology, it's not going to change much the story. And you simply count the number of words, and here, whenever you see something new, a new string that didn't appear before, you increase this counter by 1. And what you see is something like this, and here we did it up to whatever, 1 million words, or 5,000, we can actually continue it to 100 million, and it seems to grow and not saturate. So if you don't believe me, this is actually not my imagination. You put it in log-log plot, and in log-log plot it looks perfect, like a perfect straight line, which means that the whole thing more or less grows like something like a power of 0.64, which means a little more than square root.
Okay. This is natural log?
Natural.
No, it doesn't matter.
Or log base 2 or what?
It's log based whatever. It's just this will change only offset.
10 to the 10 words.
No, it's natural. I don't know.
I know. 10 to the 9.
No, okay. It's log. It's natural log. Yes, natural. Even log 2, whatever. And I'm not sure. I mean, this is something done by one of my students a long time ago. I never checked the numbers exactly.
And what is this?
No, but you know, but the history of the humankind is it cannot continue to grow.
No, but you have a billion words. Take only the news and
the y-axis.
What is the y-axis?
The y-axis is
what is the rate of
the log
of
of the number of words.
By humanity.
That's log. It's the log of this number. Okay, so it's probably log 2. 8 is about 6,000. Okay, something. Anyway, so essentially what is really important is not the constant, which may depend on many other things, like the morphology, but the exponent. This number. And so it turns out that many languages, and I can show you things for English and for Hebrew and for Korean and for whatever you want. Actually, we did it for something like 20 different languages. They all seem to obey this very simple scaling law. The number of different words grows like a little less sublinear, it's little less than 1, and usually a little more than 1/2. And this is a very regular phenomenon, which means that the number of words in a language is a meaningful quantity, meaningless quantity in the standard sense. Meaningless in the sense it's not well defined. It depends on growing all the time. So you can think about many statistical models that will behave like this. For example, if you do some sort of a constrained random walk. So that this is one basic fact about language. I mean, words are generated all the time in any language. As long as you use it, you generate new words. Okay, strange, but very, very, very systematic and very regular. And of course, it links perfectly with the idea that words are generated when we encounter new things, that we have to give them new names. And if the environment is really stochastic, and we always change our environment, so there's always new things that are going to show up there. There's another. I skipped this slide. There are two others. Some of you who heard
against stationarity in some sense, right?
It's against rationality.
Stationarity.
I
mean, there's always growth of.
Because the word cannot be deleted.
It's not really against stationarity. I'll tell you in a minute why not. I mean, if you there's two other laws that I have to mention here. I simply skipped it for some reason. One is actually very famous and completely irrelevant, known as Zipf's law. So maybe many of you have heard about it. If you actually look at the distribution of words, this is something which was discovered in the 30s by this German guy, Zipf. I don't remember his first name. He actually realized that if you plot the number of words that occur in the text only once, and then the number of words that occur in a text only twice, and then the number of words that occur only 3 times, and so on and so forth, for any corpus, and then you plot, this is what he called okay, so how many words appeared once? This is called the rank of the words and frequency of the words, and then he simply ranked them. I mean, took this column, the histogram, and plotted it in a log-log plot. It sounds strange, but you think about it, and then you get really something very similar to what I have here. This is something I did, but not on very large data. What seems to me is, again, it's a log rank versus log frequency, as they usually call it. And the frequency is the number of occurrences, and the rank is where did it appear in this list of words. And you get more or less 1 over S slope minus 1, or 1 over S, or many other. And now those of you who know a little bit about scaling laws, this is a very natural thing if you have invariance to units. What is 1 over F? No, it's triviality in the sense that it happens also for things like lengths of rivers or populations of cities or whatever. If you plot how many cities are between 10 and 10,000, how many cities are between 10,000 and 100,000, and so on, and you plot this long frequency, you get the scaling law of minus 1. And it's actually not that difficult to explain. It's simply a reflection of invariance to the units, the dimension. Why is it exactly true for language? Requires some more explanation. But this is very famous statistic. What is really interesting about it is another reflection of the fact that words appear all the time. No matter how many, what is the size of your text, most of the words, or the largest frequency is 1. The most frequency of words appears only once in the text, which means that there are many, many words that appears only once, and that's it, no matter how large the text is. And we discovered another law, which I'll explain in a minute, which is actually much more interesting as far as I'm concerned, which is that if you look at the meaningful aspects of words, which is really, so here I'm actually plotting something very similar to what Ellie did before, and believe me, without getting into too many details, and I'll say something about it, how we actually measure it, but this is an empirical curve. When we measure it, this is something which we first encountered it in the work of Noam Slonim, and then with many other students, we verified this for many other languages and so on. And what we see here is the complexity of the semantics. I mean, how many words are there measured in this funny unit of information? So think about it as the entropy of the language in some sense, of the lexicon. And this is the accuracy. How much this lexicon is enabled to give precise meaning to things. And the way we measured it is by labeling a document, by telling you what it is about. And we did it for many, many documents, and then compressed essentially the lexicon from very, very few words to the full number of words in a systematic way, which has to do with this information theoretic trade-off. So this is a description of the data, it's not a description of my algorithm. And this curve is a property of language. And what's interesting about this curve that it seems to be extremely regular, and these two things are some preliminary attempts to measure it with some rough algorithms, and this is actual bound, mathematical bound. You can calculate analytically more or less on this data. And again, if you look at it as a log-log plot, in some, after a little, just revert it and then plot it in log-log plot, you get a perfect straight line with a slope which is extremely close to. Again, we did it then with Dmitry Davidov actually for about 20 other languages, and we always find the same law. And again, what does this mean? It means that words are generated in some sort of systematic manner. We split words, or we create a new word whenever there's a need for it, in some sense, in a very systematic, regular way. Now, this type of regularities in language, to me, as somebody who thinks of himself as a theoretician, is a strong indication that actually this phenomenon of generating new words is extremely, it's governed by some simple laws. So it's not that complicated. And actually, if you know, power laws like this are usually a reflection of some what you call self-similar process. Something underneath repeats itself on different scales. And if you think about the brain again, this is a strong indication that this hierarchy of chunks and objects that we mentioned before, something repeats itself on different scales in exactly the same way. And indeed, if we think about it in terms of predictions, so if our poor organism is simply trying to make sense of the future with respect to of the past with respect to some future, and what this creature now has to do is to chunk or to cluster or to put together objects in the past of the environment that will be predictive. But now I'm making his life more and more complicated. I'm forcing it to use more and more parts and to generate higher and higher, more and more complex representations. Think about it, this is precisely what we do with language. The words in language are simply names to objects that we care about, in some sense. It's not only objects, also processes, and there are different types of words and different types of nouns, but these are all details. And again, so I can take these observations about language, empirical observation, and cast them into this very simple theory. Without telling you too many details again how I do it, I can calculate analytically. You give me the statistical environment, and I'll give you what is the optimal trade-off between complexity and accuracy in terms of predicting the future. And usually, we always get curves like this. I mean, so they have this law of diminishing returns, which means that I usually start with a finite slope, which is an interesting phenomenon on its own, and then after some linear growth, I start to curve up. And of course, if the process that I'm trying to capture is very, very easy, then with very few bits of complexity, I can capture most of the structure, which means that I go up very high. But if it has some regular complexity, which always emerges like language, this will be more and more like a power law, which means like a parabola or something like this. And of course, this has to do with what Eli mentioned before about the complexity of the representation, to sound, or to whatever it is. And the nice thing about this type of pictures is that everything here is not only well defined, but very easy to calculate. So essentially, there's three quantities again. How much information you gather from the environment, how much information you need to use in the future. And of course, this is not simply information, but it's valuable information just to make Chaim happy. I mean, it's not every bit about the future is useful, of course. And we know how to trade again between value and information, but these are all details. So what is really nice about this type of story is now you have a meta theory that can allow you to talk about perceptual hierarchies in a much more precise way. So here's a recent example done by Nori Jacobi, using some new way of formulating this principle using kernels, which makes it completely tractable from a lot of problems. And you can take a picture like this, very famous and very nice, and the Starry Night of Van Gogh, and I can ask yourself, okay, let's say that I want to do to this picture what I did to language in some sense. I want to remove information perceptually without losing meaning. Now, in this case, meaning was very simple. Nori chose simply the colors, because fortunately this picture is very not only colorful, but the colors are well localized in some sense. So there's the tree, which is dark, and there's the sun here, or the star, whatever it is, and everything. So essentially, you can now play this coarsening game, and eventually generate a curve that tells you essentially at every point on this curve what is the level of you see that you can compress it very significantly in terms of the bits that you actually need to remember, and preserve some of it in terms of the location of the colors, and generate all sorts of nice pictures on the way. So, and of course, this is just an illustration. It's not I'm not taking it too seriously. What is really nice about this algorithm is that you can run it essentially on everything. And you can apply this principle of complexity versus accuracy, and here you can show that if you choose your localized kernels, which is, as far as I'm concerned, the localized sensors, what are the things that you really care about in your low-level vision in this case, you get different curves like this, which means that, so this is some sort of a linear perceptron or a linear Gaussian model, which really gives you very little information, and eventually you can increase the complexity forever without really gaining anything new. But if you move to more localized features, you get more and more efficient accumulation of information. And of course, eventually there is some sort of an asymptotic value, which is the best you can do with any feature. And this is really the best description of this image. So here is a systematic way to generate this graceful trade-off between complexity and accuracy in a way which depends only on the data. Okay, so now we have this nice scaling of information in the world, and now I can really start to pose those challenges to the experimentalists. So first of all, I think understanding the hierarchy on first principle is something this is just a collection of curves of different languages, but essentially what we're saying here can be summarized by this nice picture. I'm looking at better than this. Imagine that our perception is always in time. So that's why I borrow the temporal aspect. Even when we see, of course it's true when we see a movie, but even when I see a picture, I do some sort of a scanning, and I move from important things to less important things. I have a temporal process of predicting more and more details, even when I look at an image of Van Gogh. So though time is not explicit there, what I argue, this is almost obvious, and actually it's, again, it can be grounded on very solid mathematics, that our perception of time and space is very non-uniform. I call it a time fisheye. Essentially, think about going far into the past or far into the future. We have this curvy space. The resolution in short times is very high, and when you go further up, both in space and time, essentially we have much less information, and of course the amount of information that we have about the future is determined only by the statistical properties of the environment. It's not something which we have to invent. The fact that I have what I call predictive horizon, so I can say more about the next minute, I can say a little less about the next hour, I can say much less about the next 10 hours, and so on. Essentially, at least for simple words, it really grows logarithmically, and this is also a mathematical theorem. Essentially, so my perception of information in terms of the number of bits that I really know about the next day is the same, more or less, as the number of bits I have about the next year, and so on. Or the day is very detailed, and then the week is less detailed, and so on. So we have this curved information structure. And if you think about time as something which is perceived by information, our perception of time is not real time, but some sort of information time, then a lot of things, this is what's a theoretical hypothesis that I would like to test, and that I need to try to challenge you with an experiment testing. But if this is true, then many things make sense. And then I know exactly how these chunks of hierarchy, both in visual perception and in temporal perception and in acoustic perception, can be formed. These are the only things that allow me to make further up prediction or long-term predictions, or use the history in a sensible way without exploding my memory with nonsense. Essentially, in order to really think about the future, which I think is what makes us intelligent and planning ahead, thinking about the future in detail, I need to form new concepts. I cannot speak about the future in the same resolution that I speak about the far future as I speak about the near future. By the way, this is something which comes also from the algorithms for planning. I mean, those of you who know something about how do we plan, so we saw something like the Bellman equation or things like this. If I don't chunk the states, then the whole thing becomes intractable. But if I do this type of chunking the future, then things become easier and tractable, and it's very nice. So what I claim is that the whole thing, the hierarchies, the hierarchy of perception, essentially seem all to be followed from this single principle. You want to optimize your memories for making the most useful prediction about it. So that's it. This is a little bit too much, but right here are experiments that I want to suggest to Ellie and to others, and that's more or less where I want to stop. First of all, I want to understand the neural origins of what we call these regular hierarchies. And so I showed you some example of regular hierarchies in language, and actually I simply don't work in vision, but the more I look at vision, I see the same phenomena again and again.
You didn't mention even one hierarchy in language.
No, the hierarchies in language are obvious. I mean, so you have phonemes, you have words, you have sentences. I didn't show them. No, I didn't show them. What I showed you is some sort of reflections of scaling. But okay, you're right. I mean, I simply didn't have time to talk about it. I mean, I had time. I didn't have time to get into detail. No, you didn't miss anything. What I just said that because if you just take this hypothesis, our perception is scaled with information at this time, then I need to give new words to the same amount of information in the future, which means that I'll need new concepts to describe tomorrow, let's say next week. Or again, this is influence of Merav and Eli that talk to me too much, but in principle I need to group together things which I simply cannot specify. And this will emerge, which will generate in hierarchy. So hierarchy is the natural, actually I claim it's the only way of really generating a useful code of the future if you have a full resolution of the far future. So this is a very natural property. So this is what I call the gestalt. So Gestalt is exactly what happened to you with this image of the woman. I mean, somehow the details disappeared, and you saw something bigger than that. This was an emergence of some hierarchy. So it's a visual perceptual hierarchy. By the way, I realized only recently that there are people who can't do it. I mean, who are really impaired in terms of their Gestalt abilities, and you can tell them forever that there's a woman there and never see it. And then same is true by the way about auditory perception. There are people. There's some sort of an impairment. I wrote it somewhere here. There are people who have disabilities in mentalization or in grouping things together. And it's a very fascinating subject for people who are interested in learning and cognitive disabilities to really identify what's wrong in the brain of this that cannot move to the higher level in the art. Who don't see the Gestalt, or don't hear the Gestalt. I mean, some people in music, I mean, in the brain and music course that Ellie and I and others are teaching, we actually have examples of the hierarchy of structures, but I know that there are a lot of people who don't hear it. I mean, who cannot go beyond the rhythm or cannot go beyond the simple melody and then see that there's actually a higher structure, the things appear. It's not obvious that it's there, but it's there. Of course, this is what, and again, so which means in my language it's going higher on this curve and doing this refinement. So this curve, again, I don't want to overload you with information theoretic concept, but moving on this curve is essentially completely equivalent to hierarchy, to a code, a finer and finer code. Now, so the experiment that I am going to challenge, so first of all, the emergence of auditory Gestalt. So this is something which I think Ellie is actually talking about. I mean, how do you make sense of simple sound in terms of larger objects? So where is this transition happening? I mean, that suddenly you hear the word and not just the bits of the sound, or suddenly you hear the piece. Suddenly you have this higher level elementalization, conceptualization, whatever you want to call it. And it's not a coincidence. I think that this emergence of Gestalt, of higher level concept is also identical to the way we're supposed to do theory in science. Concept, see the higher level again, understand it in new terms. It has actually to do with the neural code. And again, this is also not all of you. Maybe not all of you are aware of the long dilemma of the nature of the neural code. So this is one of those things that, after thinking about it for quite a few years, I believe it's what some people call red herring. I mean, the neural code should be such that it should repeat itself on different scales. And this by itself is almost imposing the structure of it, in the sense that it cannot. Neurons should allow us to. The same neuron should be able to capture fine details and large details without changing the code, and without changing the fundamental nature of the rate. So something in this code should be invariant to the scale of your phenomena, and this by itself imposing a lot. One aspect of it puts all this argument of precise timing in an entirely different light. But anyway, understanding the neural code, this is something which I find extremely challenging, but of course this by itself is not a specific experiment. But again, if you look at this thing that Ellie measured with Nahum, and we now reinterpret, we didn't show you the details, but there are spikes there, and these spikes seem to encode surprise. But this is very funny to think about it, because surprise to what? I mean, so of course the assumption here, in this very simple experiment, it was surprise to the next tone, based on nothing else, because there was really no structure in the data beyond that. It's an IAD sequence of tones. But imagine now, Ellie is actually playing, I was hoping that he will tell you more about it, but maybe in the music course, he's actually playing a lot more complex things to mice, like the ligeti and who knows what. Eventually he'll play them Brahms and I don't know, jazz. But what is really nice about higher level music, just like higher level language, that the surprise happens on larger and larger passages. We are doing some experiments like this with Adar and Eran, what's his last name? Passman, yes, sorry. From Tel Aviv with chords. I mean, we just try to see surprise in harmony and so on. So we know that there is higher and higher structure. But if this is true, the fact that we see neurons responding to surprise should be universal. It should be to any surprise. Which means that what the receptive field of the neuron depends on the pre-processing, on the number, and not on the actual firing of the neuron. So this is, to me, some sort of a paradigm that solves itself. Just by thinking, neural code is really just encoding surprise. The question is, surprise to what? And the fact that so many neurons, actually, we found that in the auditory cortex, 50% of neuron you measure.
Essentially any neuron that you measure.
Any neuron that you measure. Okay, found better than that. It seems to encode surprise to the same sound, and of course it will encode surprise to much larger objects once these larger objects are perceived. So in some sense, to me, this is the ultimate answer to the neural code dilemma. There's no code. There's firing, which reflects log probability of event conditioned on past, and what is this past depends on how complex is your perception apparatus. The question is how to turn this into an experiment. Essentially, the experiment is very simple. It's essentially what it is already doing. Play mice much more complex sound streams and see if they are surprised by what we call surprise in higher and higher on this hierarchy. I mean, when you go higher and higher on this curve of surprise. Okay, so this is what we call the, this is a mistake, I'm sorry, but the perceptual refinement. Never mind. So, in my opinion, all this list of gestalt and hierarchy experiments are one class of experiments I really would like to see. And the other one is this challenge, which I really don't know how to do it, is how to measure directly this distortion of time. So I don't know. This is really a challenge. I thought about it not that long, but the fact that, first of all, is there a way, and I'm asking, I don't know, the cognitive scientist here or the cognitive psychologist, or how can we verify that you are really reacting to something which corresponds to what I call the same amount of information about the future? How to identify those chunks in some systematic way. So I have a computational mechanism for generating chunks given an environment. How do you test that this is really what the animal responds to? So, for example, one type of experiment I would like to see is to take those chunks and put them in the context of surprising more or less, and then if indeed the animal, or the human for that matter, responds to this chunk, I'm going to measure surprise when it's absent or abandoned or whatever. And again, this is a big challenge that is interesting. I'm very interested in how are all these hierarchy impairment, I call them, related to what we call learning disability. I believe that there are strong connections. For example, I'm quite sure that people with ADD, which are everywhere, we know, have some impairment in terms of planning ahead. I mean, in terms of thinking about the future. Or maybe they know how to plan, but they definitely know how to follow this plan. So at least they need some help with this. And this, in my opinion, has to do with some sort of overload or overload of information, maybe, or some other things that prevent the cycle, the hierarchy of the cycles of information to flow as we know, so as we want. In some sense, there's some sort of cutoff on the long-term planning, which I believe has to do maybe with the dopaminergic mechanism or something else. So of course, if we really believe that we understand ADD, dopamine has something to do with it. But the other problem that is also another disability that I find fascinating has to do with the absence of gestalt, with what we call mentalization. The fact that you don't really see, you see the details, but you have problems seeing the big picture. It's known now as sometimes it appears as a communication disorder, sometimes it appears as other things, but it's something which I find fascinating. I think people should think about those disabilities in light of such a theory and see if it makes sense. Okay, that's all I want to say. And in principle, we have 10 more minutes because the seminar is going to be very soon. So if you have questions or comments or complaints, this is fine. To both of us.
Okay, so we got to this slide. Most of what you say here is not really, I cannot really translate them to concrete experiments, except for one, which is the prediction or to test the hypothesis that a single neuron will be sensitive to larger and larger objects.
Yes, that's right.
So that's a concrete experiment. I think the answer will be no, but not in every place in the brain you will have it. But that's a concrete experiment to measure. But the rest is measures of auditory gestalt. Well, that's a lifelong
No, of course.
philosophical approach. So it's not concrete experiment.
If I had the really concrete experiment,
then you know the
I
answer,
would
basically.
tell it already. I would do it.
Yeah, that's right. So,
no, but
so I think the challenge.
Starting a discussion. I don't know.
I know, but I'm just saying that the general. I think part of this encounter here is to raise more basic fundamental questions, and part of it to see whether one can actually extract from these world views that theoreticians have concrete experiments of that.
I agree. I'm well aware of the fact that this is too vague. But the fact that you actually identified one experiment here is also already more than I expected.
I think in a way that all of the discussion between Tali and me, the interaction between Tali and me regarding these things really started because we found things that look like coding of SUR5 relatively early in the auditory system.
But there was, looking to the future, Tali suggested.
Yeah. So now we play music to the rats, and we have the on the surface results that needs to be very well controlled, and in a way showing chances that can be interpreted as chances. So that's still in auditory cortex and single neurons.
Okay.
Hello.
I have the easy question.
But you have to
I have the easy question and the hard question. The easy question is that neurons and sensory systems respond many neurons in the sensory system respond quite consistently to very simple stimuli repeatedly. If you apply a click to a cell in auditory cortex, many of the cells, not all of them, but some, would respond the same way to this stimulus again and again and again by one spike. It happens.
You're saying there's no adaptation.
We like, when we speak here, we like to emphasize the new things that we find that they may not have the same response, and they have very nice responses to surprises. But if cells represent only surprises, which is what you suggested, how would you say that they respond to the same stimulus all the time? Namely, they code for minimum surprise?
No. Okay, so that's a good question.
This is the easy one.
No, but I think I answered it. What I'm saying, this is by making this distinction between learning and behaving after adaptation. So what I'm saying is that if you believe this frame, this is the separation of the equilibrium flow of information from the learning phase. So what I'm saying is that most of us don't really learn all their life. I mean, it's not true. We behave, we react to new things all the time, but we use the same mechanism more or less. It's a very slow adaptation beyond that point. And then, just like we enjoy the same piece of music even if you play it 10,000 times. By the way, I actually argue that you don't hear the same piece of music 10,000 times because you slowly climb on this curve of complexity and always hear new things there. But in principle, we can enjoy many things and forget it. I mean, don't internalize the new structure. So we are limited. I mean, we don't really learn all of it. The answer is that
the question was about coding, not about learning.
Well, okay. So SUR5 accounts for some percentage of the variability of the responses of the neuron to stimuli. The meta-surprising thing is the fact that the SUR5 accounts for a lot of the variability, but not for all of it. So, for example, the neurons in auditory cortex are still tuned to frequency. They respond to some pure tones and they don't respond to other pure tone frequencies. But within this constraint, about half of the variability has to do with the SUR5. Okay, so that's they still code other things as well, not only the SUR5.
I don't know. I didn't
This
understand
is the experimental.
Do I understand correctly that you don't agree about this?
No, I think we agree. Just you asked the question, why is it that we repeatedly respond to the same signal, even that we are not surprised?
You were stating so strongly that neurons only encode the surprise.
Well, first of all, it's a very rough encoder of surprise. Surprise conditioned on some complexity of representation. And what we see, at least in Ellie's anesthetized cats, those that we actually measured, that they don't improve their representation beyond a certain limit and stay there.
But when I see the same stimulus again and again, every time I'm surprised because maybe the prior is that there will not be a stimulus.
Yes,
What is surprise?
No, of course. So it's you're right, and that's something that we have to eventually, if we want to have a theory of everything, then we'll have to resolve. So if you play your stimuli once every 10 seconds, you will get a strong response almost independently of what the stimulus is. Okay? When you play the stimuli every 300 milliseconds with probability that and that, okay, and then you can ask why the neuron responds now a lot and different time only a little bit, and that would be related to the surprise that occurs during that sequence, okay, on a time scale of a few tens of seconds. We cannot use, at the moment, we cannot use this theory to account for everything that we see in the brain.
No, I mean, a good experiment, actually, violating the theory is even more challenging for me than confirming it. I mean, show me things which are not like this.
No, he showed you already.
There are things that are like this, but there are many things that are not like this. We showed it, like this.
What do you mean? Repeated exposure? No, the fact that
the
a monkey responds...
The cell does not respond to the surprise. 50% of the variability cannot be accounted by the surprise. I think it's more. Although I agree with all of what you say here, I think there is...
Okay, so maybe we're taking it to an extreme, right? So first of all, there are two ways around it. One, maybe it is surprise to things that you didn't measure, I mean, other things that happened there. But if I believe Eli, I don't know, I just quote him, this 50% variability is almost completely Poissonian. Actually, I don't think it's true.
Well, the response was the same.
No, it's not possible.
Anyway, I completely agree with you that this simple experiment cannot account for everything, right? But this is not violating the principle. It's violating this particular setting. I mean, the principle.
Tell me the principle and then we'll...
The principle is very simple. The brain is sitting on this curve at some level of complexity, if you allow it to adapt well enough, and the curve is analytically calculated by an optimal trade-off between information from the past and information about the future. That's it. Subject to value, subject to reward that you can. But that's it. It's a very simple.
It's too simple to be
Okay, so may I go on to the hard question, because maybe some other people...
It's not violate a simple principle.
I think some of us came from the Society for Neuroscience meeting, and there was a lecture about neuroeconomics. And the thing he most strongly tried to prove is that our predictions suck. So this was the main lecture. The lecture was about how it is very hard to predict and how economics is useless completely for economics because you cannot predict. So how can it be that our brain, which is so good in predictions, is so bad in this?
So first of all, I think that the term prediction is not well defined. Most of the time we actually make very good predictions. Of course, we are not very good at predicting the really surprising things. But those are so rare that you don't really care about it.
Because it's random.
I don't think it's true.
Because it's random.
No, I don't think it's true. I mean, just like saying that you can't predict the future. Period. Okay. Most of the time you actually make very good predictions.
I wanted to ask something.
Getting back to Chaim's question. Aisha. It's getting back to Chaim's question about the different scales. Like if you have a tone or a beep or something every, let's say, 3 seconds, I'm not surprised after the 6th tone or something like that. And I don't think there's any reduction in the response. I mean, it's like the kind of adaptation you see is very dependent on the time intervals the kind of information you see at the level of neurons in the auditory cortex is very dependent on the time interval that you introduce between the sounds, but which is not consistent with my conceptual ability to predict sounds. So, I mean, if you want to see fast adaptation, you do tuck, 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 and you see something very fast, but you do tuck, tuck, tuck. You cannot predict the next one, but the neurons are a surprise better, I think.
Well, they adapt even if you play it once every 2 seconds, which is quite slow. But at some point they will behave the way that time said. I mean, just the fact that the sound appears over a background silence will be a strong enough surprise.
No, we have decay of memory. That's absolutely. I mean, obviously we don't remember everything the same way forever. So, so this is some sort of fatigue and some sort of memory decay.
But exactly when the next tone will be presented, a bit really accurate with a very different time scale than any kind of adaptation you see within the same neuron in the auditory cortex.
I can well predict the sunrise in a scale of 24 hours, or maybe even 10 years from now. But my photoreceptors and my retina is surprised every time.
Really surprised?
Well, to a large degree. I mean, of course, I mean, there is development, there is maturation, there are adaptations on scale, but...
So, again, at least in the auditory cortex we can get as long as few minutes. And I think, I mean, I would like to be true. I'll show you the data. It's not yet controlled well enough. But this is I mean, I will not play you the piece, but it's a MIDI rendition of rate-adapted version of this piece of music. Musica Ricercata, number 2. It has basically 3 notes. Okay, there's an E sharp, F sharp, and here at this part of the piece you have a 3rd note appearing, a G. Okay, so you have a context that's created by playing this E sharp and F sharp at the beginning, and then you have this surprising note, which is a G. It's just a semitone away from the context. Okay, G, 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 G. Here they play together, and then the first context reappears. Okay, so that's. Okay, now this is, it's a very rough representation. These are average of a lot of units from the auditory cortex of rat responding to these sounds. So this is the context. This is where the G first appears, and here you have a moment in piece where the G and the E sharp and F sharp are playing together, all of them loud. These are the moment in time in which we have responses. They're all locked to the time of an event here. And basically, most of these responses come from this surprising G. Okay, so here the adaptation occurred over a time scale of about 2 minutes. Okay, and after that, a very small change in the physics, just a move of the semitone away, make the neurons in the rat auditory cortex react quite a lot. That's not 24 hours, I agree. Okay, but this is already time scales that are relevant for real life. That's not an audible signal.
But you're just saying, okay, that this rat is completely insensitive to.
Yeah, it's an appetite.
Yeah.
So, I mean, the controls are not yet in. I'm showing this a little bit in this presentation. Since Tali mentioned it, I thought it's worthwhile just to see the tantalizing possibilities. Let's really understand DDT.
Anyway, I want to thank you all for your patience, and I hope that I'm sure that the next couples will do much better. Thank you very much.
Okay.
שמעת את זה? לא. מהר מאוד לומדת את זה, אפילו לא חושבת עליה. הכל של הכל, אבל אני יודע שהוא רוב הזמן. באיזה קטע היום כתבנו אחד מתוך אין בריבוע, אחד מתוך מספר היום חושבות גדל קושור של מילים של תלמידים. וזה גם כן תופעה קצת שכל לא חושב, לא רק אז גם אחד לא חושב אולי מועד לזה שחובה שחובה אבל זה לא הכל משנה, התופעה שדיברתי באמת שבאה של כל השפה ואחד הדברים שיוצאים לבדוק עליהם מיד זה באמת בן אדם בודק ולא מדבר על הספורט של כל המילים בטקסט אני דיברתי על כמה אבל מה שאמרתי אחר כך הרזולוציה של העלייה של המילים אומרת שיש כאן מילים סף של משטר של בידוי זה קורה כל הזמן יושבים עם לב וזה כל